All right, we're ready to get started. So this is our review for our midterm 2. So again, I've discussed with you our midterm 2 covers everything after midterm 1, which starts from chapter 4 all the way to our Monday lecture, which is all the way until 6.4. All right. And today the structure is I'll go over all the concepts we went over in these chapters with a little bit more focus on chapter 4. Since it's been a while, we do all these derivations and also like definitions of things and also calculating of thermodynamic changes. After doing that, we'll do one example together, which is a highly derivation-based example. And hopefully in this process, I can show you like how do I think about a problem when I look at it. Like it might be unexpected problem. So if you feel like I'm writing down any equation, you don't know where it comes from, do raise your hand and ask. Because I want to know like what people are getting lost about. All right, I hope you can at least know how to set up a problem when you see one in the exam. So let's get started. First question, in chapter 4, at the beginning of lecture 12, we start to build a connection between material equilibrium with thermodynamic state functions. We started by talking about the second law of thermodynamics, which is entropy. The first thing we end up doing is this kind of plot of saying like, okay, so by analyzing entropy, and also like a hypothetical system with irreversible process taking place, we find out that the entropy of the universe will always increase until we reach a point that everything is reversible. All right, so we're saying before equilibrium, your ds is always larger than 0, and then at equilibrium, your ds is 0 for this isolated system. Now, if you make this isolated system bigger to the universe, then we can generalize this conclusion to be like the entropy of our entire universe is always increasing until we reach the point that entropy is maximized, or everything is dead and only reversible process is taking place. Then from there, we then define two new state functions describing material equilibrium specifically, because we want to know when material equilibrium is reached by looking at the numeric number of certain state functions. So the two things we defined are our Helmholtz energy or work function, whose physical meaning is the maximum amount of work your system can output for a like material equilibrium going on. Could be phase transfer or reaction equilibrium. So for A, we are talking about if we plot A as a function of time, note that for A, we're looking at a closed system, constant temperature and volume. Right, so for A, what we derived is that the overall Helmholtz energy will be a going down process, meaning that prior to equilibrium, my dA will be negative, so it's keep decreasing. And at equilibrium, dA will be 0 at equilibrium. Right, so in this kind of figure, we could ask different kind of question based on this figure. For example, I could give you these two figures and then remove the label on your y-axis and ask you, like, based on what we are plotting here, which state function are we describing using this diagram? All right. Alternatively, we could give you the state function, give you the shape of the figure, ask you to fill in the condition so that this figure is true. Or we give you the state function, give you the condition, ask you to plot it. Right, so there are different ways we can ask you a question, which is a conceptual question relative to these definitions of terms. Or like we can take it one more step, like hiding this A, and after you find out what A is, we have a follow-up question in what's the physical meaning of A? And you are expected to know the answer to that question. Right, so let's do that practice, right? So let's say we have this state function. which is something. And we say this is true for a closed system at constant Tp, and the curve looks like this. So we're saying like d of this question mark equals to 0 at equilibrium. So what is the physical meaning of this state function? First of all, what's the name of this state function? G, right, that's our Gibbs free energy. And what's the physical meaning? The physical meaning, that's a maximum amount of non-PV work my system can output for a reaction or a phase transfer taking place of my system, right? So non-PV work is anything that might be useful. Could be electricity or like chemical things, chemical reaction, chemical potential change, right? So like these are the questions we could ask, all right? And then in chapter 13, we start talking about thermodynamic relations, Gibbs equations, Maxwell relations, dependent of state functions. And in chapter 14, calculation of changes in state functions. So for this one, this is the equation sheet that I make. It works for me because I'm the kind of person who like to derive everything from scratch. But you can have your own version of the equation sheet, right? So whatever we discussed in class and you feel like you want to just directly use it, there's no rule of saying you cannot do that, right? But in this one, remember in thermodynamic relations, we start from the very foundation, which are these basic equations. Right, so these equations, the du equals to TdS minus PdV, this involves both the first and second law of thermodynamics, all right? And for this one, it's true for closed system, PV work only. And then we define our enthalpy, Helmholtz free energy, Gibbs free energy, based on our internal energy plus PV, or internal energy minus TS, or enthalpy minus TS. We also have definitions of your heat capacities, constant volume heat capacity or constant pressure heat capacity. And you can also rewrite this into the ds over dt version, or the ds over dt at constant pressure version. Right, so these are the basic equations. And then by using some fundamental calculus tool, so when I say this class use calculus, but we only use very basic calculus, like these are about all the calculus we used in this entire quarter. And they might appear in different forms. For example, like we went over using these equations, like for example in this case, coming up to these Gibbs equations based on the definition, right? So the calculus tool we're using are these two, like how to take differential equations of x, y, and x plus y, right? So if we're thinking about this one, my dH equals to du plus d PV, that just du plus PdV plus VdP. We plug in the du into here. We get dH equals to TdS minus PdV plus PdV plus VdP. Your PdV cancel out. You end up getting dH equals to TdS plus VdP. Right, so that's what we have. All right, so like this is a kind of question like I expect you to know. It's not hard, right? It's just like using basic calculus to convert the fundamental equations into our Gibbs equations. And then from the Gibbs equation, we have a few variations of the Gibbs equation. Again, the key point of everything on this page is we're trying to be able to describe the relationship between all these thermodynamic functions and say like, how do we link them into real life, right? So these are like abstract concepts we define that might be useful for them. We were just talking about physical meaning of Gibbs free energy and Helmholtz energy. How do we actually write out an expression of these terms in things that we can measure, right? So these are all the tools we went over. And again, we're not using super complicated mathematical equations to do that. For example, this one. Now, if we want to convert your original Gibbs equation into these relationships, what equation we're using is simply writing out the total differential equation of your Helmholtz energy as a function of T and V, right? So in this case, what is that? We have dA as a function of T and V. You write that as partial of A over T at constant V, dt plus dA over dV at constant T dV. Right, and we just look at, okay, this one, dA over V at constant T equals to negative P, dA over T at constant V equals to negative S. Very straightforward. And at the end, we have the Maxwell relations. So for the Maxwell relations, we're using the Euler's reciprocity rule, right? So in this case, we're saying if you say like my z as a function of x and y equals to m dx plus n dy, this is almost a format of my Gibbs equation, right? If we still use a Helmholtz energy as an example, my dA equals to negative s dt minus p dv. So my a is z in this case, your x is t, y is v, and then your m is your negative s, and n is your negative p. Right, you plug it in into this equation, you get the Maxwell's relations. So everything here like looks super complicated, but when you are using them, like just think about how we get it like step by step, and know like Maxwell relations and also these thermodynamic relations gives you a way to link these partial differential equations into something you can measure, right? And what are things that we can measure? We went over things as simple as temperature, volume, and pressure. Like temperature, you can simply get a thermometer and get a temperature read. Volume, pressure, heat capacities, that's are the things we can measure. The thermal expansivity and isothermal compressibility, these two are terms related to our equation of state. All right, so for example, if we can give you a random equation of state, I'm just gonna randomly write it out like P V minus B equals to nRT squared, which is not true. It's just a hypothetical equation of state, right? But how do you use this equation of state and solve for like alpha and chi? That's gonna be one of the things we might ask you to do. Alternatively, we also have the Joule coefficient, the Joule coefficient and the Joule-Thomson coefficient that linking how does your temperature change with respect to volume at constant internal energy, how does your temperature change with respect to pressure at constant enthalpy. All right, so these are the thermodynamic measurables we might discuss. But nevertheless, like I don't want to scare anyone, just want to remind you, like you did all these, right? In class, we did all these, and you know how to do it. And later on, we'll see an example question and see how do we set up the problem so that you're doing it in the correct way. All right, but before we do that, let's come back and review everything back. Calculation of the change in state functions. Well, so this one, the only thing we're using is integral calculus, right? So some of the things we were discussing about is like, if we're looking at, say, if the question is asking for delta U between your T1 to T2, effectively, you're just saying like, okay, we're just from T1 to T2, your du. More likely, this can be a process of multiple variables. So in this case, let me do this. So we know that U is a function of temperature and volume. Right, so in our previous lecture, like in the Swan thermodynamic relations, we can solve for the dependence of your internal energy on temperature and volume. Or the other way to put it, we can write my du equals to your dependence of your internal energy on volume and temperature. So in this case, specifically, I think, let me write that out. I think my du over dv at constant t is equal to alpha t over chi minus p. and then my du over dt at constant v, that's just your Cv. All right, so in a case, when we're talking about my initial state being your, let's say T1, V1, and your final state is T2, V2. It's really hard to solve the double integral where both coefficients are changing, but because my internal energy is a state function, it's the same of saying like, hey, between your initial and final state, there exists a intermediate state, which is V1, T1, V2, and then T2, V2, right? So the first step becomes an isothermal step. So my temperature is not changing. We can just considering the volume dependence. Second step becomes a isochronic step, and my volume is not changing. So we can do the integral separately, right? Or the other way to put it is we can write my delta U to be the integral of my first isothermal step. So that's become my V1, V2, alpha T over chi minus P dV. And that alpha T over chi minus P is something we can solve for if we know the equation of state. Plus the second step, the isothermal step, which is T1 to T2, Cv dt. And Cv is something we can measure as a function of temperature, and we know how to solve it. And that's generally true for any other state function as well. The bottom line here is, well, how do you write out these dependence of state functions on the variables and how to set up the integral calculations? All right. And then we moved a little bit out from all the math and derivations and start talking about chemical potential. Or the other way to put it is now we're moving out from the world that everything is reversible and at equilibrium. We're started talking about what if the two systems are not in equilibrium with each other, like material equilibrium, right? So you have phase transfer or you have chemical reactions taking place. How do we describe it? So in lecture 15, we introduce the idea of chemical potential, where your chemical potential is defined as mu I alpha. So I'm going to go really slow on this definition, so bear with me of thinking what each terms are, right? So in this case, this is a chemical potential of species I in phase alpha, and that's defined as the partial differential equation of your total Gibbs free energy in phase alpha. Note that this is the most important part, like mostly people make mistakes in this statement over partial differential of number of mole of your species I in phase alpha, while keeping your temperature of phase alpha, pressure of phase alpha, and all other number of mole of species in phase alpha that's not changing. All right, so the most part people make mistake is on here. This is the total Gibbs free energy of everything in your phase alpha. All right. Now this one, we can simplify it for specific cases. Like for example, we discussed later on is if we have an ideal gas, a pure ideal gas, we then make this statement of the chemical potential of a pure ideal gas equals to its molar Gibbs free energy. And why that is the case? Because if we're only looking at pure ideal gas, then the total Gibbs free energy then only becomes the same as your Gibbs free energy of that pure ideal gas. You only have one species in there. And it's ideal gas, it's only one gas phase. All right. But when we're talking about general chemical potential definitions, like this is the most likely part, people make mistakes, especially in true and false questions. And then we discuss what exactly is chemical potential. So in phase equilibrium and reaction equilibrium, like in phase equilibrium, we were making a comparison between your chemical potential and temperature, right? So it's like temperature, the heat flow from your high temperature body to a low temperature body. So temperature tells you the direction of heat flow. Likewise, in phase transfer, the transfer of matter always takes place from a phase with higher chemical potential to a phase with lower chemical potential. So it works similarly. And then we went over the idea of reaction equilibrium. In here, it's mostly just rewriting the Gen Chem questions into a form that's more generalized and symbolized. So we can generalize a reaction into like 0 goes to the sum of stoichiometric coefficient of all species in there for any chemical reactions. We also went over, let's say, the delta H naught of the reaction equals to the sum of your stoichiometric coefficient times the molar enthalpy of each species involved in that reaction. Now I'm going to ask a quick question here. Is my delta H naught an extensive or intensive function? We're talking about the enthalpy of the reaction, or the standard state enthalpy of the reaction. Raise your hand if you think it's extensive. Raise your hand if you think it's intensive. All right, anyone choose intensive, want to explain for everyone for the rest of the class?
The way I like to think about it is the delta H naught of T is per like cycle of a reaction. So you could either, if you have a given reaction, you can choose to run like 10 cycles of it, or like 50, or like a half.
Yeah.
They all give you different numbers. So.
Yeah, so that's one way of understanding it, of course. The other way to put it is we're talking about delta H naught, the standard enthalpy of the reaction. It's a sum of your molar enthalpy adds up together, right? So if your molar enthalpy, HM equals to H divided by N, so if your molar enthalpy is an intensive function, this must also be an intensive function. The other way to put it is that if you look at your thermodynamic table, and then you'll be able to calculate the delta H naught of the reaction from the table, and you see that the unit from that calculation is like kilojoule per mole. Right? So different ways of approaching the question. All right, so that's all of chapter 4. Any questions before we move on? No? Okay. Let's see, next one. And then in chapter 5, right, we just mentioned the thermodynamic table. So chapter 5 is all organized over the thermodynamic table. So for chapter 5, we start by talking about how to use the thermodynamic table, and then talking about how the thermodynamic table numbers come from. Right? So in the first one, we're talking about the heat of the reaction. You can calculate it from the sum of your heat of formation of each species. So these delta H, the standard enthalpy of formation of different species at certain temperature, are tabulated in your thermodynamic table. And the relationship between your enthalpy of formation and your molar enthalpy is that the enthalpy of formation is coming from your the formation reaction. Or when we say a formation reaction, it's like, let's say we are trying to get the molar enthalpy, the delta H of, it's like these, the standard enthalpy of formation is defined based on a formation reaction. So if I'm having like a random reaction of C4H8, and I want to make this molecule, the formation reaction is going to be carbon, or each element in its reference form, which is carbon in graphite, plus hydrogen in gas. And we balance the reaction as 4 goes to C4H8, which I think it's a gas. Is it? I'm not sure. But nevertheless, so we're talking about this kind of reaction, right? So the delta H of this reaction is giving you the standard enthalpy of formation. Yeah.
So we're supposed to know what the reaction is if you give us a compound?
So this is like, it always comes from elemental form, right? So the real question is, how do I know what's the elemental form of each element? So that means you go to the thermodynamic table, you find out what is the line of which the element, the heat of formation is 0, right? So there's no reaction between, like, say, carbon graphite into carbon graphite. So obviously the delta HF of carbon graphite will be 0. So you look at lines so that you can find the elements in its reference form. So let's do a practice together. Let's see. Yeah, that's our appendix table. So let's say in here, what is your reference form for iron? Well, we first find iron as my element, and we look at here. We see, okay, so that's 0 and 0 for my delta H naught of formation. So the reference form of iron would be the iron condensed, right? So if you were asked to find out, okay, so what is the reaction to form the, let's say, Fe3O2, and that comes from 3 Fe condensed plus O2 gas goes to your Fe3O2. All right, just looking for the table where it's 0, and then, like, for example, deuterium 2, so D2 is also the reference form. Yeah.
But there's also an F2 gas that's...
Is fluorine and iron same element?
Sorry?
Is fluorine and iron same elements? We're talking about the reference form for each element, right? So I know they all start from big F, and they look similar. But fluorine, then if I'm looking for, like, FeCl2, and then FeCl2 would come from Fe condensed plus Cl2 gas. Yeah. Okay. All right. What else? And then we spent a good enough time talking about how delta H heat of formation is being measured in calorimetry reactions. That's like a very long discussion of all 6 steps. And after that, we start talking about temperature dependence of reaction heat. Now, this one is something we introduced in chapter 5, but later on in chapter 6, we're saying we might come back and use these relationships. We did a derivation of saying, okay, so the change of your reaction heat, or whenever we say temperature dependence of reaction heat, we're trying to describe how does my reaction heat change with respect to temperature, right? So D, delta H naught over dt equals to delta Cp naught. And your delta Cp naught is again defined as the sum of your molar isobaric heat capacities in standard state of species I. And similarly, my delta Cp naught is also a intensive function. And in this case, if we're looking for how does your delta H naught change with respect to your, I should say delta H naught, like how does my delta H naught change with respect to temperature? So in this case, how does my delta H naught change with respect to temperature? You can take the integration of your delta Cp naught over temperature. Then in chapter 5, we also introduce, like, conventional entropy. And in this case, we start by looking at the third law of thermodynamics of saying if you have, like, a perfect, so the third law of thermodynamics and an arbitrary statement. So the arbitrary statement is imagine you have a condensed phase species that's at 0K, and it's in internal equilibrium with each other. We're seeing that S0 equals to 0. And then using the third law of thermodynamics of saying, like, at 0K, for any kind of internal equilibrium going on, the change of entropy is 0. So that's a bit of conceptual derivation we did. Basically, the point here is that entropy is a function. We know it is a form of probability. So the absolute number of entropy doesn't have a real physical meaning, right? So in this class, we're always talking about how does entropy change throughout the way. In order to do that, we must give entropy like a reference point. So the third law of thermodynamics defines that reference point, which is the entropy of the condensed species at 0K equals to 0. And then we can use everything we discussed to calculate how does entropy change from that reference point. And that is called that's the whole process that we did. Remember the SO2 example of like how do we calculate the conventional entropy of a species at certain temperature. All right, so we did a lot of derivation there, like remember, use the area below the curve to estimate how does the entropy change. And then for low temperature range, we're estimating that your delta S is roughly equals to the Cp naught low over straight. And for reversible phase changes, your delta S equals to delta H phase transfer over T phase transfer. Yeah, any questions? Oh, I saw a hand, but okay. And then we have delta H and delta S defined. Obviously, the next one is talking about the standard Gibbs free energy of the reaction. You can do that in two different ways. You can either use G equals to H minus Ts to do it, or you can use our thermodynamic table, which is your delta G of the reaction equals to the stoichiometric coefficient times C standard Gibbs free energy of formation at certain temperature and for species I. For these two parts, the most likely point people make mistake is on the conventional entropy part. So if we go back to the appendix table, and I'm just going to highlight one of the reference species like carbon graphite. So note that your standard enthalpy of formation of carbon graphite and also your standard Gibbs free energy of formation of your graphite at 298 Kelvin standard state is 0, but your conventional entropy of your graphite at 298 Kelvin is non-zero. In fact, if you look at the entire table, you'll be like none of the things in this entropy, maybe except for H plus, because it's just a proton, but everything else all have a positive number. All right, so just keep in mind, like, don't make that mistake of saying like everything, like even the element is in its reference form, its conventional entropy is not 0. Yeah.
You will be provided this table on the exam.
Yeah, or you can bring your own copy. I mean, we'll print it out for you, but if you have your own copy, feel free to use it. All right, so that's all of chapter 5. Again, chapter 5 is based on our thermodynamic table, right? So we want to be able to use what we learned and then to tabulate all the data based on experiment and the thermodynamic equations we used into this number, and then start talking about how to, what's the change of these thermodynamic functions for a chemical reaction. So that's chapter 5. Any questions before we go on? No? Okay, sounds good. And then chapter 6. Well, chapter 6 is we're finally linking all the equations to something that chemists care about, which is reaction equilibrium. Namely, we're trying to say like, okay, so now from this thermodynamic table, we can calculate delta G of the reaction. How do we link that to experimental reactions, right? So in this case, we specifically talked about ideal gas reaction equilibrium, because after all, the ideal gas reactions are the simplistic possible reactions in thermodynamics, right? So the solution phase reactions or electrochemistry, these are a little bit more complicated than ideal gas reactions. So we started by talking about ideal gas reactions. Before we do that, we spend a good enough time talking about the what is an ideal gas mixture, right? So there are two things, that's two criteria that need to be met for ideal gas mixtures involving the partial pressure of your species I equals to the mole fraction of your species I times the total pressure, and also PV equals to nRT. And then from there, we defined the chemical potential of your ideal gas species I equals to the standard chemical potential of your species I plus RT ln P partial over P naught. So in here, this one is talking about the chemical potential of your pure, the standard chemical potential of your pure ideal gas species I at 1 bar. So here it's just using the ideal gas law to address the pressure changes, that's all. Yeah.
UI naught at T is going to be like a fixed value that we're given, right?
Right, but this one we're talking about like a function of temperature, so yeah. Or the other way to put it, you should be able to calculate that, because for a pure ideal gas, remember the chemical potential of a pure ideal gas equals to its molar Gibbs free energy. And then we spend some time linking the chemical potential or the equilibrium constant to the Gibbs free energy of saying your equilibrium constant for these ideal gas reactions is defined as a product of your partial pressure at equilibrium divided by P naught to the power of your stoichiometric coefficient mu I. And we have delta G naught of the reaction equals to negative RT ln Kp. And then we also spent some good time talking about temperature dependence of your equilibrium constant, or the Van 't Hoff equation. So we went over the derivation of the Van 't Hoff equation together. So how do we use it, right? If you think about how do we use it, let's say we know the Kp naught at 298 Kelvin. I'm just going to say equals to some kind of number A. And the question asks you for Kp naught, or you want to calculate the Kp naught at, let's say, 400K. Like, what is that number? Right. So in this case, doing the analysis will be like, okay, so my delta T equals to 400 minus 298 Kelvin, and it's definitely small. So we can use the Van 't Hoff equation, assuming delta H naught is constant. Yes?
You said small is considered 300K.
About 300. It's going to be very obvious. It's either going to be like something like 100, 200, or like 1,000, 2,000. Yeah. I don't like ask borderline questions. And how do we do that, right? So the ultimate goal is how to find the Kp naught at 400 Kelvin. So in this case, that's just a little bit of integral calculus. We're looking at the ln Kp naught equals to delta H naught divided by R, negative sign, times dt. Just moving the dt to the right-hand side. And then taking the integration on both ends. You get the integration of negative delta H naught over R dt. Now this part, everything till here is just generally true. It doesn't matter how big your temperature change is. But in this specific case, we're looking at my temperature change is small. So we can just assume my delta H naught is constant. So that means this part, I'm just say your ln Kp naught at 400K minus your ln Kp naught at 298K equals to the negative delta H naught over R, and you do the dt between T1, T2. Yeah.
So for the equation that's on the board, isn't it d ln Kp over d1 over T is equal to H over R?
I think you're right. So I'll update it, but you get the gesture, like how to set up the integration and then solve it. And I'll update the annotated note. If I didn't do that, send me an email and remind me. Nevertheless, so like that's how to set up these calculations and then link it to the actual integral. And then we will be covering shifts of equilibrium, shifts of ideal gas equilibria after the midterm 2. So this part is not on there. It just, I made this before Monday, so I don't know how fast I'm gonna go. Okay, any questions? I only have 10 minutes for example questions, but I still wanna do this with you. So the question here is saying a certain gas obey an equation of state, which is P Vm equals to RT plus 1 plus BP. And the question asks you to find A, what is du over dB at constant T equals to BP squared. So ask you to prove that this is true. And B, ask you to find like CPM minus CBM equals to R times 1 plus BP squared. And C, ask you to find mu JT equals to 0. Which one do you want me to do? I only have 10 minutes. I can only do one of them. Yeah. Okay, so any other suggestions? I'll do part C and see if we have more time to do the rest of it. So, what is part C? Now, the part C, we're asking for mu JT and try to prove mu JT equals to 0. So what do we know about mu JT? So we first write down what is my Joule-Thomson coefficient, which is mu JT equals to dt over dP at constant enthalpy. What else do we know? So in this question, what else do we know is, well, somehow I want to be able to use the knowledge we have, which is the equation of state. And in this question, if we want to use the equation of state, we want to somehow translate like this enthalpy into like enthalpy dependence of pressure or enthalpy dependence of temperature, right? So these are solved problems in chapter 4. How does your thermodynamic equation change with respect to pressure or temperature for enthalpy in this case? So these are the things we know. So for example, pressure dependence of enthalpy. So that's dH over dP at constant T. Yeah.
Sorry, why is that your thought process to do that?
Okay, so I look at this question. I'll be like, for some reason, this question gives me an equation of state. And it asks me to solve for mu JT that I have no clue how does the temperature change with respect to pressure. How can I solve it? Now, what do we know in this case? We have something that is your cyclic chain rule, right? So you have 3 variables linked together. So in there, we have dt over dP at constant H, dP over dH at constant T, dH over dt at constant P equals to -1. All right, so for this question, I'm asking myself, like, what do I know and what is given in the question? And how can I use something we already solved and transfer this question into a solved problem? Like, what are my solved problems? Now, in here, this one, right? So this is 1 over dH over dP at constant T. And my dH over dP at constant T equals to negative TV alpha plus V. So that's something we already solved in the lecture note. You don't have to redo that proof if you see this. What else do we know? We have dH over dt at constant P. Now, what is that? That's one of our heat capacity, right? So that's our Cp. And in here, we have our alpha. Now, alpha is something we can solve for from the equation of state. So my equation of state, or what is my alpha? So alpha, this actually should be solved from previous cases. But let's just do that together. So what is my alpha? Now you can go back and check. You see, I don't have very good memorization. I always go back and check what they are. And my alpha equals to 1 over v dv over dt at constant p. All right. And then in here, I know that this 1 over v and this v will be canceled out, or v alpha just equals to my dv over dt at constant p. With me so far? I'm just going over with you like how I think about the process. Not in the most pretty way. My annotated note is much prettier, but this is how I think about this process. And then thinking about equation of state. Do we know how to solve this partial differential equations? We do, right? It's just rewrite this partial differential equations into volume as a function of temperature and pressure. So it'll be like, okay, so from here, I want to write V equals to RT plus BPRT divided by your pressure. And we're taking the differential of volume over temperature at constant pressure, and we can solve that. And well, the molar volume here will be canceled out. Let's see. dV. Well, Vm just equals to like V over N, so N is not changing after all, so I'm just being a little bit sloppy here. Yeah.
Why did you bring over the volume towards the
Well, because I want to solve this partial differential equation, which is dV over dt at constant P. Yeah.
Was there a reason we solved for on CP?
On the top?
Yeah, I don't know.
Well, it's just fact, right? It's just the partial differential of h over t at constant p equals to Cp. So I'll just leave it there for now and see if we come back and use it. Where am I? Okay, so this one, let's redo that. So my volume then equals to my R plus BPR divided by P. Oh, this is not my volume, this is my... And what else do we have here? We have this entire thing. So let's rewrite this one. So dH over dP at constant T equals to this one, which is negative T times V alpha, which is this one, R plus BPR over P, and then plus V. So that's coming from here. And my volume, again, equals to this entire thing. And that's my RT plus BP RT over P. And these two cancel out with each other, as you see. All right. So these two are effectively the same. That will get canceled out. And then what we have? We have that in here, my dH over dP at constant T will equal to 0. Or the other way to put it is my dt over dP at constant H equals to negative my dh over dp at constant t times dt over dh at constant p. Now, because we solved that dh over dp at constant t equals to 0, this one must be 0. All right, then this one doesn't matter. I mean, I write it out as like 1 over Cp, but at the end of the day, it doesn't matter because this term is 0. All right, it looks a little bit messy here. My annotated note is much more prettier. But again, this is how I look at this problem. And your answer on the exam doesn't need to be pretty. All right, so it's okay to have messy answer. And I'm running out of time, and good luck on Friday. Miranda will be with you on Friday. If you are confused on any questions of wording, you feel ambiguity, do ask us before you work on it.